The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
So we've already established that resonance delocalization will stabilize that carboxylate anion. Okay, so you have a base abstracting a proton from that hydroxyl group. That introduces a full negative charge at that oxygen, and that negative charge is delocalized to the other oxygen, resulting in the formation of a resonance stabilized carboxylate anion. Okay, but I want to take your attention, I want to draw your attention to the carbonyl group on its own. The carbonyl group in the neutral form of an acid. That's what we have at the bottom of the screen right here. This is a neutral form of the acid. So we've already said that this carbonyl group right here is very polar, which means most of the negative charge is around that oxygen and very little of it is around that carbon. Because of the polarity of that group, that carbon is largely already negative, and this carbon is mostly positive in nature or around it because of reduced electron density. What do you do when you introduce resonance stability? All you're doing is effectively moving the negative charge from this oxygen right here to this oxygen right here. That's all you're doing. But this oxygen already has negative charge. It's already largely negative because of the polarity of the functional group, that carbonyl group. So resonance will not be able to add that much more negative charge at this position because most of the negative charge is already there. I'm going to repeat myself. Resonance will not be able to add that much more electron density at this position because most of the negative charge is already there because of the polarity of the carbonyl group. And that's exactly what the second statement is trying to explain. The high polarity of the carbonyl group means that little charge is actually delocalized by resonance. Most of it is already there. Okay, so in that way, resonance doesn't have that much of an impact in the stability of the carboxylate anion compared to the effect of the polar carbonyl group, the inductive electron withdrawal by the polar carbonyl group. And that's exactly what you can see at the bottom of the screen right here. As a matter of fact, the structure of the resonance contributor that we have to the right, the one I'm highlighting right now, that's actually a more accurate description of what a generic acid would look like. Okay? Because of the simple fact that you already have most of the negative charge around the oxygen atom and most of the positive charge around the carbon because of bond polarity, this is a much better representation of the neutral acid than is this. So this resonance form actually probably contributes more to the overall structure of the acid than does this one right here. So, and for that reason, the polarity of the carbonyl group is way more of an important factor in the stabilization of the carboxylate anion than is resonance. So, in this case, inductive stabilization by the polarity of the carbonyl group is so much more important than resonance. And I hope you have understood the reason as to why this is the case. So we're going to move on right now. And what we are going to look at is the inductive effect of substituents. So how substituents can actually affect the acidity of carboxylic acids. Now,